Today we are going to present about scalable development of event-driven airflow DAGs. So myself, Subramanian, I'm from InvestNet. I'm managing a data engineering team. InvestNet is a wealth management tech company, and then Ipsa is my co-presenter.
Hi everyone, my name is Ipsa and I'm a data engineer at TechMetric. TechMetric is the fastest growing cloud based shop management system in the auto repair space. We are bringing in hundreds of customers in shop each month, which is providing us really exciting data opportunities as a product and company.
So for this presentation, we have divided this into three segments. The first segment is the use case itself. So this is very important so that once you understand the use case, then it's very easy to understand the solution and architecture behind it. The second segment is how we created event-driven DAGs, and the third segment is like the scalable development. So this use case itself, like we developed at InvestNet, Ipsa and I Ipsa previously worked at InvestNet, so we designed and architected and developed together when we worked at InvestNet. So let me dive into the use case. So basically, if you see this, it's like more like a data ingestion or common ingestion or data source onboarding use case. So here we'll have a lot of different sources. It's a many to one kind of use case where we'll get many different sources. We have to onboard all these different sources. It'll come different file types, different varieties, different timings, different formats. The goal is to load them into a standard data model. We'll have to do some metadata mapping, a unique ID resolution, and try to load them into a standard data model. So on the left, if you see, it's all the different sources, and then we try to load them into a landing area, and then we'll try to do all this normalization. We call normalization. It's more like the enriching all this standardization. And on the top, you see, we also integrate with different microservices. So that's on the top. So it's an end-to-end data source onboarding or a common ingestion use case. So what is so complex about this use case? It's mainly the kind of variety. The first one is variety. So there are like a lot of sources. Every source is different. Like one source will send 1,000 files. The other source will send only 5 files, and they will send it in different types, different layouts. And one source will send at midnight, and the other source will come late at 5 a.m. But our goal is to as soon as things come, we want to understand the different patterns and load them into a standard data model. So that's the first complexity is variety. Everything is different. Second is volume. Like I mentioned, there are a couple of hundred sources. How do we manage everything? How do we manage all the different files and load them into a common data model? And then we have to also handle the volume of data. If you aggregate all the sources, it's a terabyte scale on a daily basis. And then the other important thing is these sources are it has some domain logic involved. Like a developer cannot go in and go and understand about the source on the first day. So the analyst role is very important. So the BAs have the domain expertise to understand the source. So they have gained knowledge over the decade. So they know this source very well. So their dependency is also there. And then we should also have daily operations intact. We should need accurate and timely monitoring so that we can run, debug, rerun before SLA. And the other important requirement is the moment a source is available, we have to load it within 20 minutes. That was the target we had, mainly because there are other downstream applications that are waiting for this data ingestion. And it involves a complex multi-step processing involving Spark and Python, which we will detail. So to do all this within 20 minutes, the moment it arrives, and with all this variety is kind of the main requirement. So I'll just dive a little bit into the technology stack. Basically, we already have a foundation. We have everything on the AWS cloud. So our data storage layer is S3, and our metadata layer is Airtable. We use Airtable to do all this metadata management. And then we use EMR on EKS for data processing. And then for all compute, we use Lambda and EKS. And we also have a lot of microservices on traditional RDS and also on GraphQL endpoints, which has hierarchical data structure. And then finally, our data is stored in S3, which can be queried by Athena. And we also ingest data into Snowflake. And for Athena, we use Glue as the catalog. And then we also have a UI, which interacts with microservices, mainly for operations and monitoring. And this, if you see, this is kind of our tech stack. And two important pieces is like we need to have some kind of central monitoring. So that's the Neuralink, which will anything we do, we will ingest the logs to Neuralink, and we will use Neuralink for monitoring. And the most important piece we are coming is the complex workflows. So how we can orchestrate the workflows which goes top to bottom or bottom to top is using Airflow, because Airflow can do data loading from S3. It can also load to S3, can push to Snowflake, it can interact with microservices. So Airflow is the main piece which connects on the different workflows. So now here we have the kind of requirement. So what is the framework we want to build is like, we want to create a framework which is consistent. So I'll take an example on the top. So we are creating a new processor on top of Airflow operators. So Airflow provides EMR operators, EMR sensors, then it provides other EMR EKS operator, EMR EKS sensor. But we want to create a layer on top, and we are calling it processor. So that processor will, it's kind of a wrapper on top of the Airflow operators. So the whole idea of this processor is like, we will abstract it out so that for any changes, we'll have to make it at only one place instead of going and doing it multiple places. So that's the first advantage. And second advantage is it is consistent, so that the developers don't have their own flavor of developing in every DAG. And the third most important advantage is it looks very simple in Airflow, because once you start using all these different steps, Airflow can get quite complex, too many tasks. So we're just wrapping it and making it simple. So that is on the left. It's all kind of the wrapper. We are calling it as processor, which Ipsa will dive deeper. On the right side, we want to make it easy for the developers to come and plug in these boxes, the EMR processor box or the green box or the red box, in an easy way. We don't want all the developers to come and develop it again. So we want to have an easy mechanism where they go and use these already developed blocks and orchestrate it. So that's kind of the this side. So basically, we'll have two development teams. On the left is the core development team, which will try to develop the framework itself. The right side is the lightweight development team, which will use the already developed blocks, and it will try to orchestrate. So this is the high-level requirement, and now we will dive into how this became a technical product, which Ipsa will explain.
All right, so now getting into event-driven DAG handling, I'm sure you guys have heard of many different ways you can implement event-driven use cases upon file arrival in Airflow. One of them would be that you turn on your DAGs and then you have your sensors wait for files to arrive in whatever storage location you're trying to track. Other option is that you can have Airflow datasets. But in our use case, the problem is that we don't know when the files are going to arrive. Our file arrival pattern is very inconsistent. So there can be, say for example, multiple hours of difference between the first file and the last file. It is also possible that a file is coming in a couple of hours late. Now these scenarios may seem like edge cases, but in our case they're infrequent but not insignificant. So our solution was to create Airflow DAG and use Airflow APIs to mark the task status in our files as well, sensors as success using AWS Lambda. So AWS Lambda is, well, just any Python script or any other script in programming language that you can use to trigger Airflow APIs and update task status. So why are we doing it this way? Let's recap our requirement. Number one, we want to start processing as soon as the files arrive. We don't want to wait for all the files to arrive. If, say, for example, 2 out of 15 files have arrived and there's a way we can start processing of the DAG, we want to start it. Because of this reason, we decided that we will move ahead with this kind of solution. So now that we know the background, let's get into the first part of this solution. So there are two important pieces in this diagram. One is an AWS step function, which is an orchestration in AWS, which is an orchestration service in AWS. And you could be using any other data pipeline or any other orchestration mechanism that you may have in your system. And on the right side, you will see a file sensing task group, which is the first task group of our Airflow DAG. Now on the left, what the step function is really doing is it will get the files, it will validate them based on some preset business rules. Once they are validated, the files will be staged, and when the files are staged, we are ready to trigger our DAG. Now on the triggering of the DAG side, for each file we've got sensors. Now these are not real sensors which are actually sensing a location or waiting for a file to arrive. They are time delta sensor async, which basically sleep for the amount of time, for the specified amount of time, and after that they will trigger the next task. What we're doing is we are setting an SLA based on the SLA of each file. We're setting a sleep time for all of these, and they will just sleep, not utilize any resources while they're sleeping. And when our files are ready from the left side, we will go and update the task status as success for all of these different tasks via Airflow APIs. Now, how do we do it, right? You have to find, out of all the DAGs that you have to find the specific DAGs, and then you also have to find that specific execution. So how our setup is that we have one DAG per source. And for every DAG, we have a specific level of granularity at which we want to run our DAGs on a daily basis. So in this scenario, we've got our source, the date of the file, batch code, and just a random date timestamp, which is for the uniqueness of run IDs. So on the left side, if you see the trigger Airflow process, all it's going and doing is once it knows what file and what source have come in, it will orchestrate this run ID for the DAGs. And for that run ID, it will go to the specific DAG name and try to find an execution with this run ID. If that execution already exists, it will go inside the execution, find a task with that name for that specific file and mark it success via Airflow APIs. It's basically updating the task status. If the execution does not exist, it will create a new execution and then go and mark the task status as success. So this way we are making it 100% event based, and at the same time we're also not utilizing a lot of resources because the files or the DAG will not start, nothing is waiting for the files. So we have made it very customizable, very configurable, and yet very efficient in this manner. Now, before we get into the scalability portion of the solution, I want to show you what we can build with the solution that we're about to discuss. Everything that I'm going to show you is completely configuration based unless you want to add a completely new feature, which of course will require a little bit of coding. Now, when I say it is configuration based, I'm not talking about DAG factory which is like a YAML configurable way where you write your operator and a DAG will spin up. However, this is on the same lines, but this solution was created before DAG factory was released. It is in JSON format, and the configurations are kind of similar to DAG factory but not 100% similar. However, with this solution we were able to achieve 100% control on our use case, and hence it worked very well for us. Okay, so this is a simplified architecture diagram of what we were able to build with this solution. You can make it as simple or as complex as you want. If you see here on the left is your file sensing task group that we discussed in the previous slide. And on this side is a file processing task group, which is where the actual processing is happening. Now, if you see here, you've got a lot of things going on. You have some EMR jobs, you've got your Python operators, Kubernetes pod operators, you have some API pulls, microservice integration, all of those kind of things going on. So all of these varieties you can introduce for the first time, and then it's just reusing it. So from this diagram, let's take two pieces for our next slide. So the first piece is that we're going to say we've got two task groups. One is a file sensing task group, one is a file processing task group. The second piece that we're going to pick from here is that we have assumed that we have two types of processing that we want to do. One is Spark jobs on EMR, and the other option, the other processing is some kind of microservice integration. All right, so what DAG factory has done with operators, we are going to do with our custom processing units that we are calling processors. So when I say what DAG factory has done with operators, with DAG factory, you define an operator and then you define the specifics of that operator in a YAML file, and your DAG will spin up. We have done similar things, except we're done for processors, and processors are nothing but wrappers around operators. So say for example, you have like a central pipeline monitoring system across your org, and you want to have or put an update into that central monitoring system right before, say for example, when you're submitting your Spark job, or when right after you have done a microservice pull, something like that. And you don't want these kind of minor things to actually show up as tasks in your DAGs to complicate them a little more. These kind of background things, or any other use case in the background, all of them can be achieved if you're using processors, because we're defining them before we actually call the operator. All right, okay, so that is what processors is. Now on the left side is the config that we're going to write, and on the right side I'm explaining how those configs are going to be parsed. So on the left side, if you see, you've got a call API1 and a submit Spark job, 2 JSON elements. These two are our tasks. Under them, you'll see a processor which has the value call underscore API underscore 1, which is the processor that we're calling processors, right? The task group of this task is the file processing task group, which means that it needs to be created in the file processing task group. The dependencies of this task are file 1 and file 2 from file sensors stage. So when the first two files arrive, like file 1 and file 2, you want to start your task called call API 1 and maybe not wait for the remainder 10 files to arrive. So that's what that is. The second one, which is the submit Spark job, the dependencies for that one is call API 1 from the file processing task group. So once the first JSON for the first task in this JSON call API 1 is done, the second, this step submit Spark job is going to run. So that's what it is showing. Now let's see how to parse it. So you see DAGs and then DAG builder.py and then task builder.py. These are the main elements, and then we've got some helper classes like DAG operators, processor mapper, etc. So what DAG operators is that you can define your own operators or custom operators, those kind of things in your DAG operators.py. Completely optional, you may or may not need it. The second one is a processor mapper. So what it's doing is that when you say you want to use a processor called call underscore API underscore 1, it needs to be mapped to an actual class where the logic is happening, right? So that's all it is doing. It's just mapping the processor name to the actual class object. Processor1.py is where actual processing may be happening for that specific processor. So in this case, your processor1.py could very well be call underscore API .py or submit underscore spark underscore job.py, something like that. And then on the right side, you see dags.py. Dags.py is where you would want to declare your DAG. You will, for each of your source, you will write your DAG building configs, and then you will declare your DAG with the with DAG statement. The DAG builder.py and the task builder.py are the two actual important pieces here. So that is where we're going to create our different task nodes and define dependencies. So in the sequence of operations, what you may want to do is first you'll obviously create your file sensing task group, where you will create one sensor for each file, and then you will define dependencies between the two, between different task nodes in your file sensing task group. So easy, right? You just use bitwise operators and mark the dependencies. Now the second task group, which is your file processing task group, is a tad bit different than your file sensing task group, because in file sensing task group it was just sensors, it was plain marking. In file processing, you also want to do dependencies between your parent task group, like your file sensing task group and the tasks in this task group. So we are looking like across task groups. So what really, you have a description here in the presentation, in the slides. You can just go through them, but really what we're trying to do is we want to identify each task by a group ID and by the task name in the DAG. You cache that task and then you use a bitwise operator and then you put your next task after it, and that's what it is. So your objects will get returned from processor mapper. Those objects will actually run your classes. They create your task nodes. The task nodes get into dependencies and your DAG is created. That's what this is about. Okay, so this slide is kind of on the similar lines of what we discussed in the previous slide. All I'm doing is showing you a code snippet of how it would work. The code snippet on the right is of course what your developers would write. The code snippet or the JSON config on the left is what your users would write. And when you deploy these two things together, you will have your own DAGs. So with this kind of setup, we were actually able to create our DAGs and not have too many code changes be done every time you want to create a new DAG. All you have to do is go to processor mapper. If for a new feature you write a new mapping, you create a new processor.py for any functionality that you want to create, and that's it. And you just define it in your JSON config. That's your dependency management right there. All right, thank you so much.